Where's everybody? They dropped? Oh, so how was exam one? Oh, thumbs up, huh? Note to self, exam was too easy. When it will be scored? Well, I'm meeting with my TAs right after class, but they should be graded by now, I guess, since they're graded by computer. But I've been out of town, as you probably found out. So, I've been out of town. I was out of town all week. I was in New Mexico. Oh my gosh. Anybody been out in the desert Southwest? So nice out there. It was cool and the air was dry. It's like, I get off the plane in Jacksonville, slammed by humidity. It's like, whoa, how did I survive? And allergies just, exploding in my head. So welcome back to Florida, So you might ask, Colonel, how come you weren't in class on Monday and Wednesday? Okay, so what? The random walk, yes! I love it. The correct answer. Well, I talked about this issue with y'all a while back of what it takes to be a scientist. And I think, what I said about being a scientist, I think the key things are curiosity, scientists are curious people. They want to know, they see a bug and they go, wait, I haven't seen that bug before. What kind of bug is that? A leaf, a flower, clouds, the earth. Curious about everything. If you want to be a great scientist, one that stands above all the others, it's really creativity that counts for more than anything. Because sadly, I think when we teach chemistry and other science topics, we beat the creativity out of you. So you got to memorize this, got to know this equation, etc., etc. And so somehow creativity gets divorced from science. But the people whose names we mention in class, these people obviously were great scientists, but what set them apart was their creativity. They came up with a new theory, Heisenberg or Planck or Nernst, a new equation. Creativity. I'm getting to the point here. There is a point to all this. Ambition. If you want to be great at anything, did I spell that wrong? Really?
If that's an O next to that, it looks like an I.
Is that spelled wrong?
Yeah.
Ambition is spelled wrong?
Ambition spelled right. You got it.
Thank you. God, I was going to say, I got a real problem. All right. I don't care what field you're in. If you want to be at the top of your field, you're a medical doctor, you're a practicing pediatrician, whatever. If you want to be at the top of your field, you got to have ambition. That's what separates the cream of the crop from the also-rans. I'm getting there, getting close. Especially in science, ego. We are egomaniacs. It's part of being a scientist, I guess. Megalomaniacs, And finally, we cannot forget this all-important ingredient. And that's money. Research doesn't happen without money. What do I mean by that? Well, I've got graduate students up there in the lab, and I got to pay their salaries. Now, that means I got to go out and get grant money to support the research, to pay for the chemicals that we use, to pay the graduate students' tuition. I pay their tuition, by the way. And so it takes money. And in modern science, it can be big money. So that is the point of me being out of town. I have a grant from the Department of Energy. And it's on the general area of batteries. And so you accept this money, and guess what? They now own a piece of you. So there was a contractors meeting, mandatory, all hands meeting, that's what it was called, out in Santa Fe, New Mexico this week. So since I take their money, they own me, and I have to dance when they tell me to dance. And, I can't dance. But in any event, so that's where I was this week, out there, holding the tin cup out and saying, please. That's part of my job. But I really try to minimize travel when I teach this class in particular. So I may have one other brief thing this semester, but this was my major trip for the semester. All the way out to New Mexico. Beautiful out there. By the way, I got my PhD at the University of Arizona, which is the next state over from New Mexico. Write that down. You need to know things about your professors. Here's what I say about the University of Arizona. I'm glad this is on film. I went to the University of Arizona for my PhD. University of Arizona is an almost elite, almost West Coast school. Thank you. All righty. Professor Tallum, Dan Tallum, stood in for me. He teaches this course on a regular basis. He used to be the department chair, Big, powerful man, I guess. And he told me what he went over, and it was pretty much exactly what I would have gone over had I been here. But I really would like to give you my take on calculations involving weak acids. So it's going to be a little bit of duplication, but it's important, and I feel like I'd like to give you my take on it, because here's the deal. As it stands now, you use an ice table to solve the pH of a solution of a weak acid. And ice tables are a pain, and they take time. So what I want to show you today is that you don't need to use an ice table to solve for the pH of a solution of weak acid. You got to remember a few simple things, but we're going to start with the ice table. So what I want to do, and again, Professor Tallum told me he covered this, but you are going to see on quiz 2 and exam 2 a question So you're going to see problems like this. Yes, you can solve such problems with an ice table. And that's how I'm going to begin, but I'm going to show you how to make the ice table much simpler and simplify your life in terms of solving these problems. So let's take an example, and let's just cut to the chase, shall we? Step on that. All right. Now, so we want to calculate the pH of the solution of benzoic acid. First of all, what is benzoic acid? Well, benzoic acid might be represented like this. Talked about this very important idea. Put a carboxylic acid group on anything, And by and large, you create a weak acid. There are exceptions, but by and large, put a carboxylic acid group on anything, and you create a weak acid. So this is our pal benzoic acid. Now, what's that hexagon with the circle in it? What? That is benzene. What does that hexagon with the circle mean? It means it's benzene. But one thing you got to get about chemists is that we're lazy. And so, what is benzene? Benzene is 6 carbons, sp2 hybridized. Uh-oh. Geometry was not my strong suit, never was. So there are 6 carbons. Now, sp2 hybridization. Boom, double bond. Boom, double bond. Boom, double bond. Is the structure complete? What's the formula for benzene? C6H6. So in fact, so that's one depiction of benzene. Chemical formula C6H6. Now, of course, it would be just as right to move the double bonds. You could move that double bond there, bonk. You could move that double bond there, bonk. You could move that double bond there. So that depiction is just as correct as the one I had up previously. That's what the circle represents. It represents the notion that we really can't think of double bond, single bond, double bond, single bond, that these electrons, these sp2 hybridized electrons, are delocalized. And that's what that ring represents. Now, second point, we chemists are lazy. We're so lazy that we don't want to draw all these C's and H's. So every time you see an apex like that, that's a carbon atom. And every time you see nothing attached to it, that probably means there's a proton there. So this is how lazy we are. We're too lazy to write all this. So we draw a hexagon, and everybody has to know that each apex of the hexagon is a carbon atom. And then you got to count up the bonds and go, well, there has to be something there, right? There has to be something there. So we just diagnose. And since it shows nothing, that means it's a proton. That's a very important rule in organic chemistry. If you count up the bonds, so without that proton there, you'd go, 1, 2, 3, wait a minute. Carbon is tetravalent. What the heck is going on here? It doesn't show anything there. That means there's a proton there. And in fact, if we weren't so lazy, we might even put those protons there. But we're too lazy to do that, and you have to understand that. Welcome to organic chemistry, which you will take next semester. All right, so there's our friend, benzoic acid. And I told you about Kas. I said around 10 to minus 5 is your garden variety average weak acid Ka. So nothing unusual about this weak acid. It's not on a strong side. It's not on a very weak side. It's your garden variety weak acid with a Ka of 6.5 times 10 to minus 5. All right, now, boy, I think I'm going to take a picture of this. I like this.
Is that core concept part 2?
Yes, it's core concepts part 2. Please indulge me. I like this. Okay. Oh, what happened? All right. Now, and these batteries. We'll talk about the batteries that I'm doing research on in our section on electrochemistry. All right. Now, I'm going to get lazy because I explained to you how lazy chemists were. I'm going to get lazy. All right, well, first we'll show the non-lazy side. So we can write the dissociation of benzoic acid. Here's geometry, not my strong point. Benzoic acid. I'm going to just write it in the simplest way. It dissociates. Now, that anion is called the benzoate anion. Benzoate. Remember I told you before? Suffix ate typically means anion, perchlorate, iodate, benzoate, acetate, anions. When you see ate, think anion. All right, now, we know that this is very much a reactant-favored reaction. We know that because the Ka is 6.5 times 10 minus 5. And again, we talked about this earlier. That's the key thing that makes a weak acid a weak acid. As we'll find out, the vast majority of the benzoic acid remains benzoic acid. There's a tiny amount of that in solution and a tiny amount of that in solution. And that's guaranteed by the fact that this Ka is so small. All right. But I'm going to get lazy and I'm just going to write this. We'll see this depiction. I'm just going to call the acid HA. So that's my benzoic acid. And it's going to dissociate into the benzoate anion, which I'm going to call A minus, and the hydronium ion, which I'm going to call H plus. Now, Professor Thalem correctly showed you how to solve this problem using an ice table. So here we go. That's my ice table. Well, that's my line drawing noise. So in the ice table, ooh, diverged a little. So in the ice table, oh, I hate sloppy ice tables, you know. Am I doing this wrong again? I need 3. 1, right. You'd think I'd never done this before. Okay, there we go. So we got ice, initial, change, equilibrium. So, piece of cake, that's 0.2 molar, given. We initially don't have any of that, and we initially don't have any of that. So that initial means before the dissociation reaction. Now, we need something for change. Well, I don't know how much it changes, but H plus has to go above 0. I mean, we have to get some H plus, so that tells me, I'm just going to call it plus X molar. And since for every one H plus, we also get one A minus, we can call that plus X molar too. And for every one of these, you lose one of those. You make A minus by taking out an HA. And so for every one of those you make, you lose one of those. So bingo, bango, bongo. There is our ice table completed. Now, I made the point earlier, an ice table is a chemistry to mathematics translator. An ice table is a chemistry to mathematics translator. That's the chemistry. So far, all we've got is chemistry. Now we're going to go to the math. And when we go to the math we start with Ka, write it this way, is H plus A minus HA, and that's equal to 6.5 times 10 to the minus 5. Okay, so now we do what we always do with the ice table. We take the stuff we got in the ice table for equilibrium, there they are, equilibrium HA, equilibrium A minus, equilibrium H plus, and we plug into the equilibrium constant expression. So HA was X, A minus was X, 0.2 minus X, and so clearly what we got on our hands here is a quadratic equation. Now, we know how to solve quadratic equations. So we got this quadratic equation. We got this quadratic equation, x squared 0.2 minus x is 6.5. That's 10 minus 5. Now, it's a quadratic equation. It can be solved with the quadratic formula, with the caveat from the last time that I talked about this, that the quadratic formula has that plus minus thing. And so you will get two answers. One of those answers will lead to a negative concentration. It might not be the hydronium ion concentration. It could be another one of the concentrations, but one of those solutions to the quadratic equation, the quadratic formula, will give you a negative molarity somewhere. Negative molarity can't be, therefore you know that solution is wrong. So I give you that, I walked through this with you in infinite and ugly detail earlier in the semester, so I'm not going to do that again. But suffice it to say, when I solve that quadratic formula, I get x, which is H plus 3.57 times 10 minus 3 molar. Okay, now, so we just confirmed what I told you earlier. We got a small amount of this relative to the amount of base that we started with. Got a very small amount. Indeed, we can calculate now a thing called the percent ionization. All right, so bottom line is, I used the ice table, I got the quadratic equation, and I solved the quadratic equation. But there's something important to be learned here by calculating this thing called the percent ionization. So, it asks for the pH. So pH is so the problem said, what is the pH of a solution of 0.2 molar benzoic acid? There's your answer. Now, I want to calculate this thing called the percent ionization. So I'm going to define a thing called molarity HA, and that is the initial molarity of the acid added to the solution. So what I mean by initial is, again, up at our ice table, that's our 0.2 molar. That's the amount we added before we took into account the fact that some of it will dissociate. So in this example, molarity HA is 0.2 molar. So now, that allows us to calculate the percent ionization. The percent ionization is equal to that is the equilibrium concentration of the conjugate base divided by molarity HA. So you're seeing my strategy here. It's important. My strategy is this big sign with the subscript HA. That's the molarity that you added before you considered the reaction. If it's in brackets like this, that means an equilibrium concentration. All right. But how do we know that A minus? Well, we know that for every one H plus, we get one A minus. So that means that A minus also has to be 3.57 times 10 to the minus 3. So the percent ionization, sorry, I forgot the ionization, is that molarity divided by the initial molarity of the weak acid we added times 100%. And that turns out to be 1.8%. So there is a quantitative statement about what it means to be a weak acid. Less than 2% of the acid ionizes. Put another way, what would that be? 98.2% of the acid remains as benzoic acid. So I told you that's what characterizes a weak acid. The vast majority of the acid remains undissociated. We just found that only 1.8% was dissociated. All right, now, so all of this is true. You can use the ICE table, you can get the quadratic equation, etc., etc., etc. But this low percent ionization tells you something important. What is that something important? Let's take our quadratic equation. Let's take our quadratic equation that we derived from the ICE table. So I just had this up there. H plus squared is that's the 0.2 molar minus H plus. Oh, wait, hold on. It was initially X, right? But from our ICE table, we know X is the concentration of H plus. It's also equal to the concentration of A minus. So we can write this equation H plus squared. Now, that is the molarity of the weak acid. That is the molarity of the weak acid. Boom. There's the most general way to write that equation. And we learned something very important from that percent ionization. That percent ionization tells you, that low percent ionization tells you that the equilibrium concentration of H plus is going to be much, much less than the molarity of HA. That low percent ionization tells you Most of the benzoic acid is sitting there as undissociated benzoic acid, and we only get a tiny amount. And you can see that because we solved for it. That was 0.2, and this was, what's my number? 3.57 times 10 to minus 3. We just solved for that. So it's over 2 orders of magnitude smaller. Now, that's important because that now allows you to simplify your life. Damn. Got away from me. That allows you to simplify your life because so this is our key assumption. The key assumption. If we assume the equilibrium concentration of H plus is much, much less than the molarity of HA, then that means we can neglect H plus in the denominator. Meaning this equation just got a lot simpler. Boom. Not necessary. Now, your book introduced this notion when we talked about ice tables before, this notion that if you have two things that are together, either in a sum or a subtraction, if one is much less than the other, it doesn't change the answer. So I'll put it to you this way. Let's say I gave you $1 million. Sounds good, right? Yeah. So here, I stack them up for you here. I don't know how much space $1 million $1 bills would take. Somebody calculate that, please. But here they are, right in front of you, $1 million $1 bills. Now, if I said to you, hey, would you give me $1? You'd probably say, sure doesn't make much difference whether I have $1 million or 999,999,000. See what I mean? It's of no consequence to you. You've got $1 million $1 bills. I take one of them away. It doesn't change your wealth at all, appreciably, right? You'd give me that $1, right? Okay, thank you. So you see the point. That's the whole point of neglecting a term in a mathematical. Here's $1 million. Here's her $1 million. Here's that one little dollar she gave back to me. Well, it just doesn't matter whether you count that or not. She still got very, very close to $1 million. So that's the notion of neglecting a term in a mathematical equation when two things are either a sum or a difference. Or put another way, you got your $1 million and I give you one more dollar, you say, what's the difference? You already gave me $1 million. But you'd still be grateful for that dollar, wouldn't you? All the right answers. All right. Now, and is this the very important point? Is this assumption often true? Yes, it is often true. Why is it often true? Because it's a weak acid, because the percent ionization is really small. So for me, this is your starting place right here to solve So if we make that assumption, then that makes our equation H plus squared is divided by the molarity of HA is equal to Ka. And that is a really simple equation. So see how simple it got? I don't have to solve the quadratic equation. I got this very simple equation that you can do on a $2 calculator. And so if I do that, I plug in my Ka, which was what? What's my Ka? 6.5? 10 minus 5. And my molarity HA, I take the square root, I get I get 3.60 times 10 minus 3 molar. Now let's go back and compare this. What we got from the quadratic equation we got so you can see there's very little difference between these numbers. So key point, when I solve problems like this, if I'm asked to solve, and believe it or not, we do this all the time in my lab, we're always interested in the pH of our solutions. So you make aqueous solutions, you throw things into that aqueous solution, pH is going to change by and large. And, you know, there are obviously exceptions. If you just throw in sodium chloride in, pH won't change much. But throw interesting molecules to do some chemistry for you, and the pH of that solution changes. And we want to know what the pH of that solution is. So what I always do is start with this equation. So what's the molarity? If it's a weak acid, what's the molarity of weak acid? What's the Ka? And I'll get this answer. Now, the question is, we got the key assumption here. We just made that assumption. Now we got to ask ourselves the key question. Key question. Because what we like to do on an exam or quiz is give you a problem where it is valid and maybe throw in one where it isn't, just to see if you're paying attention. So it becomes important now to ask to see if this assumption is valid, because if the assumption is not valid, then you just calculated the wrong answer. See what I'm saying? Now, in our case, it was valid, and the answers were almost identical. But the assumption might not be valid, which would make that answer wrong. And so here's the simplest way. So your book teaches you the 5% rule. I got a simpler rule. So you remember your book has the 5% rule. Does that sound familiar to you? They say, well, the 5% rule would be if the concentration of H plus from simple equation divided by the molarity HA times 100% is less than or equal to 5%. So if the H plus that you calculated from that simple equation divided by the molarity of HA times 100% is less than or equal to 5%, then you generally make the assumption, you say assumption is valid. But it's not quite as simple as that. It's not quite as simple as that. I don't think your book tells you this, but it's not quite as simple as that. So that's the so-called 5% rule that your book teaches you. I'm going to give you the 400 rule, which is more, I can derive it for you, but I'm too lazy. I'm a chemist. I told you chemists are lazy, did I not? So I could derive this equation for you. It's real simple to derive, but instead of the 5% rule, you will be always correct with this rule. the so-called 400 rule. Does your book teach? I don't remember if your book now teaches the 400 rule. I'm going to call it the Colonel's 400 rule. You know why I'm going to call it the Colonel's 400 rule? Because I have a huge ego. Come on. I told you that at the beginning of the class. I mean, you got to have a huge ego to talk about yourself in the second person. You know what I mean? I mean, you know, that's a huge ego thing. So, if the molarity of HA divided by Ka is greater than or equal to 400, the key assumption is valid. So the 5% rule your book teaches you, it's not quite as simple as that. This you can take to the bank. If the molarity of HA divided by Ka is greater than 400, your key assumption is valid. So that then gives us a general strategy for solving this problem. So we began with the question, how do you calculate the pH of a solution of a weak acid? And here's the way I do it. Assume the key assumption. Okay? 1, assume the key assumption is correct. 2, that allows you to use this simple equation. And then 3, check assumption. Is that H plus that you just calculated divided by the molarity of HA greater than or equal to 400? So, if it is, then you're done. If yes, where am I at? 4. If yes, you are done. Yes? Oh, I'm sorry. Oh, thank you. Yes, thank you for noticing that. I screwed up. Thank you. Greater than or equal 400, the 400 rule. If yes, you're done. If no, solve quadratic. And so for me, rather than doing an ICE table, it's just much easier for me to remember this equation. So again, what I'm saying is, yes, you can use the ICE table and you can get the quadratic equation. You can solve the quadratic equation exactly. You can do that. But I don't do that. I assume the key assumption is correct. I use that simplifying equation. I check to see if the 400 rule is obeyed. If the answer is yes, I'm done. If the answer is not, I'm going to solve this quadratic equation. And for me, it's just easier to remember that equation than it is to go through and work the whole ICE table again. But either way is valid. You can do it any way you want. But this way is easy for me. All right, that's all I wanted to say on weak acids. Let's stop there.